طيب بسم الله الرحمن الرحيم. حياكم الله يا شباب. We will inshallah continue our discussion في in moving from all the discussion في cryptography into discussing software security. What do we mean by a secure software? إنه fundamentally when we say a secure software, we basically mean two يعني basically important things. الشيء الأول is that the software behaves as the designer intended, right? So when someone develops the software, the piece of software needs to behave and act the way that the writer of this software intended to. So if the writer of the software intends this software to basically securely method and gives you and manage your passwords and never communicate or send those passwords anyhow, this is how the designer of the software do it. But also another important component in the software needs to behave as the user expects it. So going back to the example of securing passwords, if the user uses a software to manage the password, so the designer intends that it, have all the passwords together in one place, use it, store it, whatever, and the user expects to do this, and those passwords never get shared by the designer. So if the designer creates a piece of code that takes all the passwords method and puts a copy of the passwords in the designer and the creator server, with the user not having an expectation for it to do so, this means that the software is not secure. معناه there is no vulnerability actually in the software itself. No one have hacked it. Like the designer and the creator of the software, him or herself, actually made it act in a way that the user does not expect. So two things are really critical when we talk about secure software. So what are the common software vulnerabilities? How do softwares or programs get actually breached, get hacked? What are the reasons? What are some of the most common vulnerabilities that we see out there? So there's obviously the most very common buffer overflow. We have issues with input validation, the format string problems and the integer overflows. And we're going to talk about each one of those in the upcoming couple of slides. So we start by a buffer overflow. So buffer overflow happens when the software in the buffer creates some space in the buffer, and then it ends up the data get created outside the space without the software stopping that relationship or this data from continuing to overwrite. The C and C++ programming languages are the most common ones to have buffer overflow. And they are very, very common programming languages because operating systems are being built using those languages. And those languages give you really good performance because they give you super strong control over the software. So many programs, many operating systems are built in C, C++, browsers are built in C and C++, and because it gives you really strong ability to control different pieces and optimize and have really absolute control on the behavior of the software. And it puts all the effort of the security on the programmer side. So why do we actually care? Okay, who cares if the software overwrites some additional data in the memory? We have, abundance in memory. Well, we care because it could write other buffers that are adjacent to this and change some of the data and the variables there. It could overwrite the variables themselves. It could overwrite the method and the stack pointer, the things that are control the way how the program actually behaves. And we're going to get into a little bit more details here in a couple of slides, how do actually a program behave and why does it use the buffer. And it could result in many, many weird things. One, it could result in unexpected program behavior, termination, incorrect results, or actually manipulating some programs to behave in a way and expose some internal data. طبعا أول ما, one of the first people that actually popularized the concept of buffer overflow is a guy called Al-Swan, and this smashing the stack for fun and profit in 1996 became a really, really popular paper that talks in details with step-by-step discussion. How can you actually break the stack for gain as an attacker and someone trying to hack into different systems? And the first worm, Morris worm, in 1988 used a buffer overflow vulnerability. So it was really age old, but however, we actually continue to see buffer overflow are pretty common vulnerabilities. So how do programs behave? You might have seen this if you took any programming class. The stack grows from up to down, and then you have the code segment in the memory, you have the data segment, and then you have the heap, and the heap basically grows from bottom to up. And the stack keeps in it the flow of function calls, the subroutines. And every time there's a function call, the stack basically stores that snapshot and jump to another piece and load stuff and start executing. Heap creates dynamic variables. Data keeps the global and static variables in it. And code basically stores the piece of code, like the static piece of code that is used to run the logic of the program. So there are multiple different kinds of buffer overflow. We have the ones that use shellcode. We have ones that are overflow function pointers. There is return to libc attacks, which overflows the return address in libc. And there's the off by one, which basically causes the program to oftenly crash. So how does exactly Linux process uses the stack? So we have the Unix process, uses the stack, as we said, it grows down. And then there is the ESP, the stack pointer that points to the next block, next empty block to be used in the stack. So if you want to use the next immediate block in the stack, you go to ESP, and then the stack grows it grows here and then grows, goes up and down, and it grows and then goes down. So it's a contiguous pieces of allocation. Then we have that section for shared libraries. All the shared libraries sit on the stack in a preserved section. And then we have obviously the heap to continue to grow from bottom to up, right? So this is how a Linux layout works. If we go into a specific stack frame that keeps a very specific when you call a function, how do you pass variables? And you should have studied this in operating systems. This is just a simple review. It's you have, when another function wants to create a function call, first thing that it does, it puts the parameters in the stack, then puts the return address, which is the next address that needs to be executed when the program finishes running this. And then it puts the old stack frame pointer that existed before the new data here came, right? So the old stack frame pointer here, comes, and then all the local variables in that function get created in the stack, and then the new stack frame will have the immediate available data point, or like available address in the stack. So when, function, when you call something like this, right? And then let's say there is like statement 1 here. And then if you go to, f is, int, whatever. So we know it has 2 variables, right? And then maybe it has, like a char, called variable, right? Let's say we have this. So when like this function, when it's calling f, the first thing that it does, it puts a and b here, and then puts the return address, which is the address of S1, right? And it puts the previous stack frame pointer, which is supposed to be the address, the first address of the parameter here. It should go here. And then the local variables, which I have the char, let's call it C, right? So I have C here. And then the new stack pointer is basically the next available address after C. So this is how a stack frame basically works. And this is like a practical example here. Put the string here because this is a string which is saved as a pointer to a char. So this is actually not the whole string, but the address pointing to the string, because this is how C and C++ work. I put the return address, which is the address that right after executing function is going to go after the previous stack frame pointer. And then I put this buffer, which is 128 bytes here, 128 chars, and the char is an 8-bit and a byte. So what this function is doing is basically saying, hey, take this string as input and create an internal buffer, copy the string from this, the address of the string to the buffer, and then do something with this buffer, right? So what happens if the string basically is more than 128 bits? And we know in C and C++, if you have 128 like this, you can save 127, and then the 128th bit becomes the /0, which is the last piece of the string. So if we have this, we know we're going to start filling this data, right? And then when we get here, fill the space 128th, 29th, 30, 31, 32, 33, 34, 35, 36. So we basically start to overwrite some very, very important data here in the stack, which is super dangerous, because this data, I know exactly what should be the stack frame pointer when I leave this function. What should I put in the stack frame pointer? And here the return address, it should tell me after I execute this function, where do I go? I need to go to what is written here in the return address. So it actually starts to be, if you overwrite this, starts to be like super dangerous. So here's one thing that an attacker can do. So an attacker can basically start to put something in string, feed this function, the function, this one, I start to feed it something. And this something becomes larger than the string, and it starts to overflow the stack frame pointer, and then also change the return address, where I tell this function, and then also inject some code here, where I give it the return address, go where this code actually, this new code comes. So after you're done with this function, the first thing that you should go to is execute the code here in the stack. So when function exit, if I put here something like this, execute \bin \sh, and I make the return address goes here, after I execute function, I will immediately get the shell. And the code is basically in the stack. I'm executing a code in the stack. And how do I know what is the return address? You know, I could either guess or start to use, like, you know, the old return address plus or minus, and start to do things until I really hit the correct return address. And like we can see right now, why sometimes you use some software, you use some information, like you have an Apache server, if it has a function that is vulnerable, and that function can cause, like, you know, some issues, then I have the ability to basically inject some data that gives me some shell in the Apache server, for example, of a targeted organization. What are some of those unsafe C library functions? Like we have, you know, strcopy, strcat, getS, scanf, printf, all of this, it copies one data from the other. So this is exactly like, you know, the example that I gave. You know, imagine you have a web server running Apache, it takes a URL. So basically you know, override it and get a shell on that server. So one very quick way to address this, like, you know, the reason that this works is because the attacker can execute code that is in the stack. Well, now we know, like, if we go back, you know, all the way up here, we know that code basically should not be living in the stack. The code lives here, and if I want to execute code, it should be in that code memory segment. There should be no code in the stack. So to avoid that first example of a buffer overflow, what I could make is tell the operating system, look, if you get code that lives in the stack, don't execute it. So I could create something called an unexecutable stack. So I tell it, look, there is this code. You have this in the stack. If you see any code in the stack, don't execute that code. And then basically, if someone overflows the buffer again, like the way that I did it here, and inject some code in the stack, in, like, you know, inside code for P, the operating system starts to load this code and then realize, oh no, like this code is coming from a stack, then I should not execute that code, and it just terminates. So what happens is the program can crash, but it cannot be, like, it cannot be overridden by other things, right? So, okay, this is one example of buffer overflow, but can we create some code where buffer overflow does not require, can we attack some systems and inject some and do a buffer overflow where I don't require to inject the code in the stack? And this is what is called return to libc. So we saw earlier in I want the return to code to come here. But what I could do is, instead of returning to the code in the stack, I could know what is that system like address as a system library. It is a library, right? And I basically call this function. I put the return address of system, and we know system is exactly like running, if you, whatever the input inside the system will be run in the command line. So I call system, and the way that I give it the variables, just like how I would do variables in the stack, I would just include in system those parameters to say, please run a command on the shell by running this, by executing this on the shell. So notice here, when the operating system wants to execute, system as a function, the system call function is not in the stack. It is in the library of different system calls. So that's fine. And the system gets a parameter here. So even if I have an unexecutable stack, this would not help me to avoid buffer overflow. I can still get buffer overflow because of I am calling a system library and giving it a parameter, and it basically ends up giving me a shell access again. And this is fundamentally how this could work. I overwrite this, I put the arguments, put it here in the local argument, and make a jump, and then it goes to the return address of those arguments, and it takes it, and voila. Like, that's amazing. That's a local variable. It works. It run a kind of like basically an execution of a shell that you would get as someone who's trying to attack a system, and then start to run whatever commands they have. And this requires a little bit of crafting. When we had the ability to, basically do some laps, what happens, I used to give students some code, and I tell them, hey, you have unexecutable stack, try to create a shell from injecting data to a certain code. So another thing that actually to alter the execution of the code is you go to function pointers. We know the way that you basically save functions is that you put the pointer of this function. And sometimes inside C and C++, you can define some variables, right, as pointers to functions. And what I could do as well, instead of simply using a library or injecting code in the stack, I can manipulate this function pointer to make you jump to another function pointer that basically a place that I created myself. Maybe it exists in libc or some other places. So you might be wanting to go to a function that exists in some certain part of the code segment. That's what I could do is alter that, overwrite it with the Stack Overflow, and send you all the way to some other places to execute some other piece of code. So, and this is what is called the function pointers overflow that can cause all that problem. The final piece of buffer overflow is what is called off by one. So you guys remember when we talked at the beginning that when I do this, I have spaces. Obviously, I have from 0 to len -1. But we know that len -1 should take the backslash. Oh, sorry, it's not this one. It's this one, I think. Yeah. No. It is this one, the \0, which is saying this is the last piece of the string such that the operating system knows when the string is ending. So one problem that a programmer could do like, this function, for example, is taking an input, creating a local buffer, and then it's seeing the size of the input, and it's checking, is the size smaller or larger than the length, which is this one? And if so, copy. And if not, just skip and return and don't copy. Maybe give an error message, but here we're not giving an error message. So if the length is, let's say input has exactly the same line as length, right? So str, this one, they're equal to each other. So we would know that buffer length, and if we overwrite it, we basically screw things up, because we know for a fact that actually we can only do from 0 to len minus 1. So if we're doing buffer length, this is even already beyond the buffer. So we're off by 1, which means we're offsetted by 1 variable that is actually creating some problems. And what happens here in this case, the program just simply crashes, because you're writing some data outside the buffer, and then the buffer starts to get confused, and the operating get confused, and then they crash because you're overwritten some data. So how do you basically find buffer overflows, right? So sometimes you write a piece of code, there are multiple people who wrote this piece of code, or sometimes you forgot to check the length. You forgot to basically do the proper security check-in, or multiple team members are writing this code, and you want to make sure that you can't just line by line review it, because that would take a lot of time, but also at the same time you're gonna miss things. Even if you review line by line, your eyes might start to miss things. So this is the whole concept of fuzzing. So what fuzzing does, it starts to take a piece of code and create hundreds of millions of different inputs. Long, short, small, number, text, characters, unprinted characters, all kind of different combinations, and feed it to this piece of code. And every time, they do something like that, they try to put some piece of code that is very, very distinguishable, like, $5 size, or, 3 after each other. And if with a certain input, the program crash, they say, oh, like, hang on a second. You knew that if you gave it this input crashed, but you have no idea where did it crash, right? So one solution is you could do debug, but if you're using inter-process communication and multi-threading and multiple crazy things that are happening, debugging might become a nightmare and might be even useless, right? So what do you end up doing? Saying, oh, let me do a memory dump, let me do a core dump, and search for that symbol. And when you search for that symbol, you would immediately know, oh, this symbol was in this variable. This variable goes to this function goes here, and here's where a copy happens. Then, oh, I need to go and check the size and make sure, and then you immediately find where the problem is. There are lots of tools today, and this is, some of the people who try to find vulnerable software, مثلا, bug bounty finders. So there are like multiple companies that tells you, here is a piece of software. If you find some errors with it, and if you're able to hack it, we'll give you some money, right? We'll give you an award, we'll give you whatever. First, you need to take their permission to do fuzzing, because if you do fuzzing without the owner's permission, this is classified as hacking. And if you do it, they can sue you and create some problems, and you hacked this and yada, 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 and basically run into a lot of trouble, right? But what you could do, if they tell you, fine, here is the agreement, sign these agreements, and if you find a vulnerability, you have to tell us. There are some people who have built their own fuzzers or built, multiple fuzzers and joined them together and do that fuzzing all the time. And most of the big companies, مثلا, Google, for example, before we add any code, like when I was working at Google, the thing is you have to make it go through the whole fuzzing thing, right? لأنه that fuzzer need to try many different inputs and then basically make sure it doesn't crashes. And there are, as I said, like multiple tools that exist today that you can use for your own software. So how do you basically prevent from buffer overflow attacks? Well, one is you could use a safer language. Instead of C and C++, you might use languages like, Java, Python, other languages that have better buffer protections. The problem with those languages is they typically have less performance and less flexibility because they limit you from doing some things, but for a better security. You could use safer library functions. So instead of using strcpy, you might use, I don't give examples here. You might use something like strncopy, which you don't simply give it the target and the destination buffers, but you also have to give it as a variable the number of like bytes to transfer. So you always have to think about this and not just simply copy. You could use some static code analysis. So those are a piece of software that go through the code line by line. Whenever they see any buffer manipulation, you're copying from buffer, copying to buffer, doing things like this, they check the previous code and make sure you are checking the size and not simply and blindly doing the copy. Another thing that you can do is as we said, non-executable stack. And we saw how this solves in some kinds of buffer overflow, those buffer overflow, caused by injecting some code. Another thing that we can do is something called a runtime checking. So what that means is, so I think I go through, okay, I'll go. So this is, I've already talked about this. There are like, Vera code and Coverty that does statically checking the source code, but here is an example of a stack guard. So what a stack guard does, and it will look like, look, also before we create the space of all the variables, we're gonna add some random information here, something called the Canary method, right? So if you overwrite this data to change the return address, to change things like here, you're going to overwrite this Canary. And if you overwrite this Canary, when we look at this stack before doing any calls, we immediately check if this Canary has been erased, right? Or overwritten. And then I immediately kind of like, oh, wait a second. Let's stop because someone have did a buffer overflow. And you do it for like every frame that you do it. And this is like, tools like stack guards and things like this that you can have in place. So how to choose a Canary? You could choose a random Canary, which is basically like a random number that you add, or you could use something called the terminator Canary, which is you force the buffer to end by adding like a 0 or \0 such that no one can force the buffer to basically do all of that work in overflowing all that buffer, right? So these are just examples. The problem with something like a stack guard, you need to recompile the source code and include stack guard. It has some performance effect, but they are not that large. There are new things like a point guard, which protects function pointers and set jump buffers, for example. However, Canary don't always give you a foolproof protection because there are some advanced attackers that basically do a two-step process. They understand the Canary, rewrite it down. They can do some predictive analytics and guessing of the Canary. So there has been some attacks, even with Canaries, sophisticated attackers managed to basically overcome all of this. Also, you know, the other thing that you can do, you know, what we've seen before, it's always about protecting things in, you know, not injecting code in the buffer. But the return to libc, all what we needed is to basically have the address of something like the system function and jump to it. And if we have the address to the system function, this is great, we jump to it. So what some protections do, like the ones of, you know, randomization of address, you go like every time you load the code, right, into the buffer and you execute the code, we're gonna have random new addresses for, you know, all of those system functions. And we're going to create and create some level of you know, artificial, you know, manipulation to all of this, such that if the attack works once, the next time you load the code, you need to recompute the system address, the system function address, right? So every time, even if you find a vulnerability and able to crash one program, you can replicate it in all different programs, okay? And it makes the job of the attacker a lot more complex because they need to guess the correct address every time, right? And this is how, you know, like something like Slammer that infected Microsoft SQL servers used the same code, the same address in all the machines, because at that time we did not have, you know, memory address randomization. But if Slammer today, the same code get purged, Slammer cannot do this because Slammer, you know, guessed the address of system once, and it used it in every other copy of the attack. So what an attacker can do, like, you know, they need to guess every time that randomization. Another option, an attacker can, you know, jump and spray and do like a library of possible different addresses, and then the code can run multiple times until it hit the right one. So it actually makes the job of the attacker a lot more difficult, but the attacker can basically overcome this, right? This is basically how an address space layout randomization works. Instruction set randomization goes actually even a step further. We go, look, we're gonna randomize actual functions with a key before you get the executable, and the same key before the processor execute. The problem with this instruction set randomization is it requires some change at the operating system level, where and then you have to manage all of those keys. And we always know, like, whenever we introduce keys introduce a whole set of new problems. How do we keep them secret? How do we share them? How? Lots of other issues, right? But it's something that exists in theory, and it has been, you know, done in theory, but not in real life practice. Okay, so any questions?